Hello everyone. So, today we will consider boundary layer flow over a flat plate with uniform wall heat flux condition. So, in last lecture we considered uniform wall temperature condition, but today we will consider uniform heat flux boundary condition. We wish to determine the wall temperature Tw as a function of x and the local Nusselt number. So, let us consider this flat plate. Y is measured perpendicular to the flat plate, your free stream velocity is u infinity and temperature is T infinity. Up to x equal to x naught it is insulated, so it will be maintained at temperature T infinity as there will be no heat transfer. From x equal to x naught you can see this plate is maintained at uniform wall heat flux Q double prime W. So, your thermal boundary layer thickness will start developing from x equal to x naught and hydrodynamic boundary layer thickness will start developing from x equal to 0. So, these are the assumptions: two dimensional steady incompressible laminar flow with constant properties, insulated section of length x naught, uniform wall heat flux condition x greater than x naught, negligible viscous heat dissipation and no internal heat generation. So, in last class already we have derived the energy integral equation. So, that we will use and we will first find the temperature distribution using third degree polynomial and we will put the velocity distribution and temperature distribution in the energy integral equation and we will find the expression for thermal boundary layer thickness and then we will find the wall temperature distribution as well as local Nusselt number. So, you can see this is the energy integral equation already we have derived. This right hand side minus alpha del T by del y at y is equal to 0, this we can write q double prime w by rho Cp, because alpha you know k by rho Cp and q double prime w is minus k del T by del y at y is equal to 0. Hence, this right hand side can be written as q double prime w by rho Cp. You know that in this particular case q double prime w is constant and rho Cp are the properties and that also are constant. So, right hand side is a constant term. However, you can see here temperature Tw, wall temperature Tw will be function of x, because along the x your Tw will increase. So, as q double prime w is constant, you can find the local heat transfer coefficient H, okay, as q double prime w divided by Tw minus T infinity. So, you can see T infinity is your free stream temperature and Tw is function of x, okay, and q double prime w is constant. So, this is from Newton's law of cooling we have written. Now, Nusselt number you can find as h x by k. So, you can see you can write q double prime w divided by Tw minus T infinity into x by k. Okay. So, this is the expression for Nusselt number. Now, first let us consider a third degree polynomial for temperature distribution and we will find the coefficient using the boundary conditions. So, assume a third degree polynomial for the temperature profile so T, which is function of x y, we can write C naught plus C1 y plus C2 y square plus C3 y cube. So, these coefficients C naught, C1, C2, C3 are function of x. So, now we have boundary conditions at y is equal to 0, okay. Y is equal to 0, you can see your heat flux is given. So, you can write minus k del T by del y at y is equal to 0 is equal to q double prime w. Okay. So, you can write del T by del y at y is equal to 0 is equal to minus q double prime w by k, and at y is equal to delta T you have temperature T infinity and also temperature gradient del T by del y is equal to 0. So, at y is equal to delta T you have T is equal to T infinity, and also you have at y is equal to delta T del T by del y is equal to 0, because that is the free stream temperature. So, there will be no gradient, and another boundary condition will derive from the energy equation satisfying it at the wall. So, at y is equal to 0 you can write del 2 T by del y square is equal to 0. So, you remember in last class we have done u del T by del x plus v del T by del y is equal to alpha del 2 T by del y square. So, this is your boundary layer energy equation. So, at wall you have u is equal to v is equal to 0. So, if u and v are 0, so obviously left hand side terms will be 0. So, del 2 T by del y square will be 0. So, now you have 4 boundary conditions and 4 coefficients. So, those 4 unknown coefficients you can find satisfying these boundary conditions. So, del T by del y you can write as C naught C1 plus twice C2y plus 3 C3 y square del 2 T by del y square you can write as twice C2 plus 6 C3 y. So, you can see at y is equal to 0 you have del 2 T by del y square is equal to 0. Okay. So, if you satisfy this from this equation you can see C2 will be 0. Okay. Then at y is equal to 0 you have del T by del y is equal to minus q double prime w by k. So, this is your del T by del y. So, at y is equal to 0 if you satisfy, so last 2 terms will become 0. So, that will give C1 is equal to minus q double prime w by k. And now you see at y is equal to delta T you have del T by del y is equal to 0. So, at y is equal to delta T you have del T by del y is equal to 0. So, if it is 0, so you can see from this equation you will get 0 is equal to C1 is minus q double prime w by k, C2 is 0. So, you will get plus 3 C3 delta T square. So, that means from here you will get C3 as q double prime w by 3 k delta T square. Now, another boundary condition you apply at y is equal to delta T is you have T is equal to T infinity. So, from this equation you can see you can write T infinity, okay, C naught C1 is minus q double prime w by k delta T, C2 is 0 and C3 you can write plus q double prime w by 3 k delta T cube and delta T square. So, you can see this will be C naught will be your T infinity plus 2 by 3 q double prime w by k into delta T. So, we have found 4 coefficients. Now, you put it in the temperature expression, then your final temperature distribution will be for these boundary conditions T x y is equal to t infinity plus 2 by 3 delta t minus y plus 1 by 3 y cube by delta t square into q double prime w by k. So, this is the general temperature distribution. Now, at the wall, if you want to find what is the temperature variation, then you put y is equal to 0. So, at y is equal to 0, t is equal to T w, which is function of x. So, you can write T w x is equal to T infinity. Okay. So, if you put y is equal to 0, so these two terms will become 0. So, you can write 2 by 3 q double prime w delta t by k. Okay. And also you can write T w x minus T infinity as 2 by 3 q double prime w delta t by k. Okay. So, now you can put it in the Nusselt number distribution whatever we have found. So, Nusselt number we have written Nusselt number x is equal to q double prime w x divided by k into T w x minus T infinity, right. So, if you put T w x minus T infinity this expression, so what you will get q double prime w x divided by k. So, you will get 2 by 3 q double prime w delta t by k. So, you can cancel q double prime w, then k k. So, finally, you can write this Nusselt number as 3 by 2 x by delta t. Okay. So, you can see in this expression Nusselt number, now you can find once you find the thermal boundary layer thickness delta t. Okay. So, once we find delta t by x, then you will be able to find the local Nusselt number. So, what we will do now? We know the velocity profile, we know the temperature profile, we have the energy integral equation. So, you put it in the energy integral equation, then you will be able to find the thermal boundary layer thickness delta t. So, you can see we have the velocity profile already we have derived using third degree polynomial, and from that solution hydrodynamic boundary layer thickness we have found delta by x as this. In today's class we have found the temperature distribution for the given boundary conditions, and this is the energy integral equation. So, now you put the value of u here and value of t here. So, you will be able to find what is the thermal boundary layer thickness. So, you can write d of dx, okay, 0 to delta t. So, this is your u expression, right. So, you can write u infinity 3 by 2 y by delta minus half y cube by delta cube, then t minus t infinity. So, from here you can write, so t minus t infinity as q double prime w by k 2 by 3 delta t minus y plus 1 by 3 y cube by delta t square, okay, into dy is equal to q double prime w by rho Cp. So, in this expression you can see q double prime w is constant. So, this q double prime w you can take it outside the integral and you can cancel, right. So, this q double prime w can cancel, and this k you can take in the right hand side. So, in the next step you can see we can write d of dx, okay, 0 to delta t. So, now you multiply this 3 by 2 y by delta with these 3 terms. Okay. So, what you will get? So, you can see this you will get delta t by delta into y minus 3 by 2 y square by delta plus half y to the power 4 delta into delta t t square. Okay. Now, you multiply this term with these 3 terms. So, you will get minus 1 by 3 delta t by delta cube into y cube, then plus half y to the power 4 by delta cube, then you will get minus 1 by 6 y to the power 6 divided by delta cube delta t square, okay, into dy, and right hand side we are taking this k and u infinity, okay, because these are constants. So, you can take it outside the integral and you take in the right hand side. So, you can write k by rho C p, okay, and divided by u infinity, and k by rho C p is alpha, right, thermal diffusivity. So, alpha by u infinity. So, now you integrate it. Okay. So, if you integrate it, so you can see you can find. So, at y is equal to 0, this will become 0 anyway, and y is equal to delta t we will put after the integration. So, we will put d of dx, okay. So, delta t by delta. So, if you integrate y, so we will get y square by 2. So, we will put the limits. So, delta t square by 2 minus 3 by 2. So, it will be y cube by 3. So, that means delta t cube by 3 delta, okay, plus half. So, it will be y to the power 5 by 5. So, that means 1 by 5 delta t to the power 5 by delta into delta t square. Then you will get minus 1 by 3. So, you will see it will be y to the power 4 by 4, right. So, it will be delta t by delta cube. So, delta t to the power 4 by 4, okay. Then you will get half. So, y to the power 5 by 5. So, delta t to the power 5 by 5 delta cube minus 1 by 6. So, it will be y to the power 7 by 7. So, 1 by 7 delta t to the power 7 by delta cube delta t square, okay. So, we have put the limits and is equal to alpha by u infinity, okay. So, now you simplify it, you cancel some terms. So, you can see here these 3 will get cancelled, and you can write finally d of dx, okay. So, you take outside delta t square, okay, delta t square you take common, then you can write half delta t by delta minus half delta t by delta plus 1 by 10 delta t by delta minus 1 by 12 delta t cube by delta cube plus 1 by 10 delta t cube by delta cube minus 1 by 42 delta t cube by delta cube is equal to alpha by u infinity, okay. So, you can see this first 2 terms. So, it will get cancelled. So, you have 1 by 10 delta t by delta, and this you will get as d of dx delta t square. So, 1 by 10 delta t by delta, and another term you will get as 1 by 140 delta t cube by delta cube is equal to alpha by u infinity. So, now we will assume that Prandtl number is greater than 1. So, if Prandtl number is greater than 1, then you know delta t will be less than delta, okay. And from this expression now we will neglect the second term in the left hand side. So, you can see we are assume Prandtl number is greater than 1, and for Prandtl number greater than 1 you know delta t by delta will be less than 1. So, in this particular case you can see that your thermal boundary layer thickness will be less than the hydrodynamic boundary layer thickness. Okay. So, if it is so, if you compare these two terms, then you can see 1 by 140 delta T cube by delta cube will be much smaller than 1 by 10 delta T by delta. Okay. So, neglect this term, okay. This term you neglect. So, you can write d of dx, okay, delta T cube by delta is equal to, so neglecting this term you can write 10 alpha by u infinity. Okay. Let us integrate this. So, this is ordinary differential equation. So, you can integrate it and you know that at x equal to x naught you have thermal boundary layer thickness delta T as 0. Okay. So, if you integrate it, so you will get integrating the above equation integral d of delta T cube by delta is equal to 10 alpha by u infinity. You can see these are constants, okay. Integral dx and you have one integration constant. So, you will get delta T cube by delta is equal to 10 alpha by u infinity into x plus c, and we know at x equal to x naught, okay, you have delta T is equal to 0. So, your thermal boundary layer thickness starts from x equal to x naught. So, here at x equal to x naught delta T is 0. So, from here you can see C will be your minus 10 alpha by u infinity into x naught. Okay. Hence, you can see that delta T cube by delta as 10 alpha by u infinity into x minus x naught. Okay. So, you can write delta T as 10 into alpha by u infinity x minus x naught into delta to the power 1 by 3. Now, let us put the expression for hydrodynamic boundary layer thickness delta that we have already found from solving the momentum integral equation. So, you can write delta by x, you know this is your root 280 by 13 1 by r e x to the power half, right. So, this is the expression we have. So, now you can see you can write from this expression delta T by x, okay, delta T by x. So, we are dividing by x. So, if you divide the right hand side by x and if you take inside this power, so you will get x cube, right. So, you can write 10 alpha by u infinity will get 1 by x cube, because we have divided by x and we are taking inside the bracket, okay. And here if you take outside x, so you will get 1 minus x naught by x, okay. And we have delta. So, delta you can put as root 280 by 13, okay, then x by r e x to the power half, okay, to the power 1 by 3. So, you can see you can find delta T by x as, so here you have x square, okay, and so if you rearrange it, so you can see you will get 10 root 280 by 13, okay. So, alpha is k by rho Cp, okay. So, k by rho Cp. So, what we will do? So, you can write alpha and you divide by kinematic viscosity nu, and you can write nu by u infinity, and you can see here x square is there and here x cube. So, it will be x, then 1 r e x to the power half you have, and then 1 minus x naught by x, okay, to the power 1 by 3. So, you can write delta t by x. Okay. So, you can see here what is this expression? This is here 1 by root r e x, right. So, 1 by root r e x and here r e x to the power half. So, it will be 3 by 2. Okay. So, it will be 3 by 2 and here alpha by nu is Prandtl number. Okay. So, you have Prandtl number is nu by alpha. So, and R e x is your u infinity x by nu. So, you will get here 1 by Prandtl number, here you will get 1 by R e x and R e x to the power half you have. So, it will be 1 plus half means 3 by 2 and outside this bracket if you take, then it will become root R e x. So, you can see you can write it as 3.594 divided by Prandtl number to the power 1 by 3 R e x to the power half, okay, and 1 minus x naught by x to the power 1 by. So, after simplification we have now derived the expression for delta t by x. Now, once you know delta t by x, now you will be able to find what is the temperature distribution and what is the Nusselt number. Okay. So, if you put this delta t by x, then you can get your wall temperature distribution as wall temperature variation as T w x is equal to T infinity plus 2 by 3 delta T q double prime w by k. So, if you put this expression, then you will get T w x is equal to T infinity plus 2 by 3. Now, delta T you put this expression. Okay. So, it will be 3.594 x divided by Prandtl number to the power 1 by 3 R e x to the power half 1 minus x naught by x to the power 1 by 3 q double prime w by k. Okay. So, hence you will get T w x is equal to T infinity plus 2.396 q double prime w by k 1 minus x naught by x to the power 1 by 3 x divided by Prandtl number to the power 1 by 3 R e x to the power half. Okay. So, this is the wall temperature variation. Okay. So, you can see from this expression that it is function of x, right. Now, let us find what is the local Nusselt number. Already we have written local Nusselt number in terms of the thermal boundary layer thickness. So, if you remember, we have already derived this expression local Nusselt number nu x as 3 by 2 x by delta t. Okay. And now, we know the expression of delta t by x. So, you can write 3 by 2 1 by 3.594 Prandtl number to the power 1 by 3 R e x to the power half and 1 minus x naught by x to the power minus 1 by 3. So, if you rearrange, you will get Nusselt number as 0.417 into 1 minus x naught by x to the power minus 1 by 3 Prandtl number to the power 1 by 3 R e x to the power half. Okay. So, this is the Nusselt number expression we have found for Prandtl number greater than 1 using the approximate method, because we have approximated the velocity profile as well as the temperature profile. So, this is valid for Prandtl number greater than 1, okay, because we have assumed delta t is less than delta. So, you can see we have finally derived in today's class this delta t, okay, in terms of hydrodynamic boundary layer thickness delta. Then putting the value of delta, we have found delta t by x, and you can see it is also function of Prandtl number and Reynolds number, and putting this expression in the wall temperature variation, we found this is the wall temperature variation, and then we have found the local Nusselt number as this. Now, let us consider a special situation when there is no insulated region. Okay. So, that means x naught is equal to 0. So, in this expression you can see, if you put x naught is equal to 0, then you will get the expression for thermal boundary layer thickness, wall temperature variation, and local Nusselt number for the unheated region as 0. So, you can see in this particular case x naught is equal to 0. So, thermal boundary layer thickness and hydrodynamic boundary layer thickness starts developing from x equal to 0. Okay. So, in for this special case, in earlier expression, if you put x naught is equal to 0, where you have plate with no insulated section, then we have already found delta by x, then this is your delta T by x, putting x naught is equal to 0, and delta T by delta, if you can see that delta T by delta, if you put, then you will get as 0.775 divided by Prandtl number to the power 1 by 3. Okay. And wall temperature variation, you can see here you will get as T infinity plus 2.396 q double prime W by k into x by Prandtl number to the power 1 by 3 r x to the power half. Okay. So, you can see it varies with x. Okay. And Nusselt number x you will get as 0.417 Prandtl number to the power 1 by 3 r x to the power half. In this expression you can see, does TWX increase or decrease with distance x? You can see that you have here REX, okay, one x is there and also here x is there. So, you can see that your wall temperature will increase along x. So, if you, although in this particular case you have this plate with uniform wall heat flux, but TW which is function of x will increase along x. Okay. Now, let us see what is the accuracy compared to the exact solution, because in this particular case we have used approximate method, where we have approximated the velocity profile as well as the temperature profile as third degree polynomial. So, we have found what is the thermal boundary layer thickness as well as the Nusselt number. Now, let us compare these with the exact solution. So, you can see for Prandtl number 1, exact solution delta T by delta should be 1, because delta T is equal to delta for Prandtl number 1. But from the integral solution you can see for Prandtl number 1 delta T by delta is 0.775. So, error is much in predicting the thermal boundary layer thickness, it is 22.5%. Now, if you compare the Nusselt number with the exact solution, so this is the exact solution. Okay. You can see Nusselt number x is equal to 0.453, Prandtl number to the power 1 by 3 r x to the power half. So, this is your Polhausen solution, okay, with unheated region. So, you can see this is the expression, but from the approximate solution we have found 0.417 Prandtl number to the power 1 by 3 r x to the power half. So, you can see error is almost 8%, but it is Nusselt number is predicting well, right, but here delta T is having much difference with the exact solution. So, in this particular expression you can see your REX is your u infinity x by nu, right. So, you have, so that means your in the denominator you have root x and this is your x. So, that means TW, okay, varies with root x. You can see. So, this is in the numerator you have x and in the denominator you have root x. So, in the x by root x it will be root x. So, TW varies root x. Now, if we assume a variable temperature profile, okay, in the flat plate, then can we get back the same expression of Nusselt number whatever we have got assuming the constant wall heat flux boundary condition. Okay. So, let us see that. So, now we are considering laminar boundary layer flow over flat plate with variable wall temperature. So, you can see that your wall temperature varies with root x. So, we have taken this flat plate where temperature varies as T infinity plus C into root x, where C is your constant. Okay, C is equal to constant, and in last slide we have seen that generally for constant wall heat flux condition TW varies as root x. So, we have taken TWx is equal to T infinity plus C root x. So, you have free stream temperature T infinity and Prandtl number is greater than 1, so that delta T is less than delta. Okay. So, for this expression if you use the third degree polynomial for velocity profile, so we have already derived this, delta by x we have derived this, temperature profile. Now, with these boundary conditions, if you see that we have in the last class we have used uniform wall temperature boundary condition, and for that we have found the temperature profile. So, same temperature profile we can put it where TW is function of x. So, you can see this is the same expression what we have derived already for uniform wall temperature boundary condition, and this is the Txy, but here Tw is function of x. So, Twx plus T infinity minus Twx and 3 by 2 y by delta T minus half y cube by delta T cube, and this is your energy integral equation, right. So, now in this expression you put u and t. Okay. So, already this we have derived, and here already we have derived this, but here Tw is function of x because your wall temperature varies like this. So, if you put it and you will get u infinity is constant. So, we have taken outside d of dx. Okay. So, you will get from this you can see it will be t minus T infinity. So, you will get Tw minus T infinity. So, if you put the expression for u and T minus T infinity, so you will get this expression, and right hand side you can see del T by del y. So, from here del T by del y you just find at y is equal to 0. So, these terms will become 0. So, you will get alpha into Tw minus T infinity, okay, divided by 2 delta T. So, if you see these two terms, okay, and we have used Prandtl number greater than 1. So, that means delta T by delta will be less than 1. So, in this particular case you can see you can neglect this term, okay, because this term will be much less than the this term, okay, and Twx minus T infinity is C root x, okay. So, this if you put it here you can see you will get this expression, okay, and it is easy to integrate because you can see here you can put the expression for Tw minus T infinity as C root x, and after simplification you will get this and integrate this above equation and put the boundary condition that at x equal to 0 you have delta T is equal to 0. So, you will get a delta T like this expression, okay, and if you rearrange this you will get delta T by x as 3.594 divided by Prandtl number to the power 1 by 3 or x to the power half, and Nusselt number if you find it will get 3 by 2 x by delta T, and Nusselt number x you will get this, and you can see that this is the same expression as we derived for uniform wall heat flux condition, okay, and you can see the temperature profile whatever we have got it from the uniform wall heat flux condition. So, here you can see if you take from Rex this root x outside, then you will get x by root x and it will be root x, and all other terms are constant because q double prime w is constant, k is constant, Prandtl number is constant, and here fluid properties and velocity are constant. So, all these will be constant. So, you can write Twx is equal to T infinity plus C root x. So, you can see that keeping the flat plate at uniform wall heat flux condition or keeping the flat plate as variable wall temperature where wall temperature varies as root x, both will give the same result, because you have seen that Nusselt number expression and these delta T by x expressions are same in both the cases. So, in today's lecture we considered laminar flow over a flat plate with uniform wall heat flux boundary condition. So, q double prime w is constant on the flat plate, however, you have Tw which is your wall temperature varies with x. We considered initially up to x equal to x naught as a unheated region, and from x greater than x naught, it is maintained at a uniform wall heat flux boundary condition. Then we found the temperature profile using third degree polynomial. Applying 4 boundary conditions, we found the 4 coefficients, and finally this velocity profile as well as the temperature profile we put it in the energy integral equation, and integrating that equation we got finally the expression for delta T by x, which is your delta T is your thermal boundary layer thickness. Once you got the expression for delta T by x, then we found the wall temperature variation Tw and local Nusselt number NUx, and putting the x naught is equal to 0, that means there is no unheated region. Then we found the as a special condition what are the expression for delta T as well as the wall temperature and Nusselt number. Next we have considered variable wall temperature boundary conditions. So, we have taken the wall temperature variation Tw as T infinity plus C root x, and putting that wall temperature condition and using third degree polynomial of velocity profile and temperature profile, we have found the same thermal boundary layer thickness as well as same Nusselt number. So, we have seen that both conditions are same. However, if you maintain the variable wall temperature Tw is equal to T infinity plus C root x, it is equivalent to maintaining the flat plate as uniform wall heat flux condition. Thank you.